right. Well, thank you everyone for coming back. It's nice to... All right. Thank you everyone for coming back. I appreciate you being here. Today, well, I guess before we get into it, we did some leveling up over the weekend. A couple of things. So as I said last class, I had been going wireless for my internet connection, but now it's wired through a power line adapter. So that kind of runs the internet electrons, I guess, through the walls in the power cords that I have running through the house. So hopefully that gets us a little faster. I also spent not insignificant amount of time with Time Warner on the phone over the weekend. So my internet connection has been upgraded as well. And I hope that these two things combine to get rid of these audio issues that we've been having. If that doesn't work and it continues to persist, then maybe we can think a little bit about moving to a different platform. We could trial out using Blue Jeans, but since we're already here in Zoom and we've been using it this long, if we can avoid it, I'd like to stick on the same platform to eliminate confusion. Just a reminder, so office hours today from 10 to 11 and from 3 to 4. I did see a couple people in office hours today from 3 to 4. So if you are going to join the office hours, it might not be a bad idea to shoot me an email too. I know that that Zoom only lets a meeting stay open for maybe half an hour with no one in it. So if you plan to attend office hours, if you can give me a heads up with an email and a time that works for you, that would be good. If these times don't work for you, please let me know and we can try to work out a solution. What I'm going to try to do, I posted on my courses, that we'll try to meet in the same link, so the same room that we use for the class, just to try to minimize confusion. One of the things that I did this week, so I got an email from a student just asking when the homework was due because I hadn't opened the assignment box till this morning. So in light of that, I've delayed the homework due date until tomorrow and not today at the same time. So you'll have an extension of a day on the homework just in case there was some confusion over when that was due. So hopefully people are progressing with it. I think that the lecture today will help a little bit because the lecture today is all about interpolation. So before we get started, does anyone have questions about sort of the homework or what's going on in the class? Okay, if not, we will move right along. So we know that we're trying to solve the first law for closed systems, and a key part of that is figuring out where to look for data so that we can find specific internal energy, right? And if we're talking about water or refrigerant, usually the first question we're going to ask is, what's the phase? So are we going to be in sort of some liquid water regime, some steam, right? So if this was water vapor, or some mixture of the two, right? And remembering that the mixture is some combination of saturated liquid and saturated vapor, remembering that if we have saturated liquid or saturated vapor, it means that we're sort of at the temperature that boiling happens for a given pressure, or at the pressure that boiling happens for a given temperature. So we need to figure out, are we two-phase? Are we superheated vapor or are we subcooled liquid? And my advice to you would always be to look under the vapor dome, right? So are we two-phase? If we're given, say, temperature and pressure, are they the right temperature and pressure for boiling to happen? And if not, where are we on this phase plot? So the example, which you can find if you like on the My Courses webpage, but if you don't have it, that's okay because we'll go through everything here. But if you would like to have a look at it, it's helpful because it has the state table on it. So here we're kind of role-playing, I guess, that we've started a new co-op job at a nuclear power plant east of Rochester. Your supervisors completed a number of thermodynamic measurements at the plant and as preparation for an upcoming maintenance program. Your supervisor has asked you to complete the thermodynamic property information from the measurements. you're to supply the information and sketch the points on a PV or a TV diagram. So they give us the information in a way that I probably wouldn't like if I was the co-op in question, because I want to have things on a table. But this is often what happens when you're an engineer, is you're talking to someone who, somebody who wants an answer, right, or wants a particular piece of information, and they just give you the information in the way that makes sense to them. But the way that makes sense to them isn't always the way that we want it. So in this case, we have a list of values. So we have, we know that the mass is in kilograms. We have a pressure, a temperature at state 1, a pressure and a specific, or an equality at state 2, pressure and temperature at state 3, temperature and quality at state 4, temperature, and they tell us it's a saturated liquid at state 5. This one's a little tricky, because when they tell us it's a saturated liquid, that is enough information to fix the state. This is kind of a sneaky way of telling us that the quality is 0. So when the quality is 0, we have all saturated liquid. And when the quality is 1, we have all saturated vapor. So here, this is telling us that X is equal to 0. At state 6, we're given a pressure in megapascals, and we're also given a specific enthalpy. Now, we haven't worried too much about enthalpy, but it's a property, and we can use it for linear interpolation between two rows on our tables. Right? So just as an aside, we have this property called enthalpy. We will become very familiar with enthalpy as we move through the course, particularly as we start to talk about open systems. So we're not worried about it too much right now, but it's very much like specific internal energy in that it tells us how much energy is locked up in some bit of mass at a given state. The units are just like specific internal energy, so they're kilojoules per kilogram, or if you were in imperial, this would be BTU per pound's mass. So it's still an intensive measurement of energy. It turns out that as we work through the class, we're going to see, as we develop an open version of the first law, that we'll have a term that looks like this: the specific internal energy plus the pressure times the specific volume. Now, what we learned in engineering is that we want to be efficient. So if we've fixed any state, then we know the specific internal energy, we know the pressure, and we know the specific volume. And for any given state, all these pieces of information will always be the same at that particular state. So instead of having to look up 2 or maybe 3 things on a table, what we've done is we've created these tables with extra columns for specific enthalpy so that we would look less things up, right? So we're not lazy as engineers, we're just efficient, right? Because it's a pain to keep looking things up when we don't have to. So specific enthalpy is just another measure of internal energy, but it includes not only sort of the internal energy, but also this term that's pressure times specific volume. So that's got something to do with that pressure work, like that integral of PDV that we've been talking about. So I guess the thing that's important to know here is that it's not necessarily an independent property, right? So it's a function of the specific internal energy, the pressure, and the specific volume. So we still need 2 independent intensive properties, and just because you know 2 things doesn't necessarily mean they're independent. So we always have to think about what a particular property is. So in this case, for this problem, we have this handout, and we have 6 different states, right? And we're going to want to find the temperature, the pressure, the specific volume, and the specific internal energy. And maybe we'd want to find specific enthalpy too, since we looked that up. Right? We're asked to plot all these states on a PV diagram and to plot all these states on a TV diagram. So here's a picture. Remember, this is to scale. So if you're drawing things on your homework or whatever, don't worry about drawing it to scale. But this is a picture of a PV diagram, right? So it's got pressure on the vertical axis, specific volume on the x-axis. It has a vapor dome. If you want to bring, if you want to use some colored pencils or something on your exam, I think it's never a bad idea. But here, right, so we're color coding the vapor dome, where on the left-hand side, we have this blue line. If we're on that blue line, we have a saturated liquid. We have this red line on the right-hand side of the vapor dome. And if we have that, we have saturated vapor, right? That's the bounds of our vapor dome. Now, I also, just in pen here in green, I've also drawn a constant temperature line on this PV diagram. Constant temperature lines on PV diagrams slope down as we go left to right. So this is decreasing. Under the vapor dome, temperature and pressure are constant, so it stays flat under the vapor dome. And then again, it slopes down to the right of the vapor dome. If the temperature goes up, this curve shifts upward. And if the temperature goes down, this curve shifts downward. We have a similar thing for our temperature versus specific volume diagram. Again, don't worry about making this to scale. We have temperature on the vertical axis, specific volume on the horizontal axis, and we have a vapor dome. But now if I draw my constant pressure line, it slopes upward as I move from left to right. So here, if I was working on the same pressure, what would happen is my temperature would increase, right? So I get my water out of my tap at 4 degrees Celsius. I'm staying at the same pressure. I put it in my pot. I'm starting to boil it. Temperature goes up. Eventually, I get to the boiling temperature, right? Or the saturation temperature. Then the temperature is going to boil, or the water is going to boil until we get all vapor. And then what's happened is the pressure is going to go up if my system stays closed. The pressure is constant. But to stay at vapor, then we have to the temperature is going up if we stay at the same pressure, right? So the temperature starts to run away after we boil all the liquid. Again, if pressure goes up, this line shifts up. And if pressure goes down, this line shifts down. So we're given information about 6 different states in this problem. So I want to draw a state table. My state table generally looks like this, right? So I'm going to have the state number, so all these different states. Eventually, when we're doing first law analyses, just like we did in the homework, we're going to start moving between states. So as we go from state 1 to state 2, that would be one process, and 2 to 3, that's another process. But here, we just want to fix a bunch of states. So the first thing that I do on my state table is I write down the information that I'm given. This is kind of encouraging when I do this, in this case, because I know that I need 2 independent intensive properties to fix the state, and in each row in my table, I have 2 pieces of information. So I'm hoping that here in state 1, I'm not under the vapor dome, right? And in state 3, I'm not under the vapor dome, because if I'm not under the vapor dome, temperature and pressure are independent, and then I'd be able to fix all of these states. So let's start looking through our tables and see if we can fix all these states and find the information that we're asked to find in the problem. Right, so here we state some assumptions. I don't know if really any of these assumptions are actually applicable to this problem. This is, maybe it's a bit overkill. But if we were doing a first law analysis, which we will eventually do for big long state tables like this, then we'd have to think about some other things like our particular pressure volume relationships appropriate. Do we have to assume things like closed systems or kinetic and potential energies are negligible? So let's start by looking at the first state. So we know that we have a temperature of 460 degrees and a pressure of 80 bar. So we need to figure out, we know what's in our system. We know that it's water in our system, but we need to figure out what phase is it, right? So is it a 2-phase mixture? I always like to start in the middle, because then usually if it's not a 2-phase mixture, I can figure out if I'm to the right of the vapor dome as steam or to the left as liquid, right? So here, I look for the properties of saturated water, right? And here I know the temperature, right? So the temperature here is on the left. And this temperature here maxes out at 374, right? And my temperature here is higher than that. If I look back here, my temperature is 460. So that tells me we're above the critical temperature. So there's no way that we can be under the vapor dome here, right? Because our temperature is too high. We can't, at equilibrium, have a vapor and a liquid existing at equilibrium. So we know it's not under the vapor dome. But I don't know if it's too high or too low, right? So one of the things that I can do is I can look at the other two-phase table here, and I can see, try to find which pressure is the pressure that we're talking about here, right? And in our case, the pressure that we're looking for, 80 bar, is on the table. Now, in this two-phase table, what happens here is the second column, this is the saturation temperature. That's the temperature that water's going to boil at if we're at that pressure. So if we're at a pressure of 80 bar, water boils at 295 degrees. But here we're at a much higher temperature than that. So I got to think, does that mean that we're liquid water or that we're water vapor? Right? And I can sort of bring this back to kind of our common experience at atmospheric pressure. Right? At atmospheric pressure, the saturation temperature would be 100 degrees. Right? So we know that if the temperature is above that saturation temperature, we're in the vapor region, right? And that's true here too, because for the pressure that we're at, our temperature is higher than our saturation temperature, so we must have vapor and not liquid, right? Oops. Sorry about that. So here, right, because we're above this saturation temperature, we know that we must be superheated vapor. So that means that, if we were going through a process at this same pressure, right, we would have boiled up all the liquid water and the temperature would have started to run away on us and we get this steam, right? So that means we have to go to table A4 because we're talking about water that's superheated vapor. So if I'm drawing this out on my TV diagram, I'm going to be in the superheated vapor region, this red region here. So now I look through table A4. Table A4 is a series of different tables. So I got to find the right table, which is the table that has the pressure that I'm interested in. The nice thing here is that there is a table for the pressure that I'm interested in. So that's good. I don't have to interpolate between pressure. Now that I have that table, I say, okay, what's my temperature at state 1? That's 460 degrees. I look now on the temperature column here, and I see that 460 degrees is between 440 and 480 degrees. In an ideal world, my temperature is right on this row, right? So I could just read the data off. This means I have to interpolate between 440 and 480. Now, 460 is not too bad because it's halfway in between. So that means I could take the average value of all of these properties, right? So I know that my temperature is 440 plus A times 460. This should be 480 minus 440. And T1 is 460. So here I can work it out and I can find that A is equal to 0.5, right? Now in this case, probably you knew that just by looking at it. But if it's a case that's maybe not so simple, then you can work this out using math. So now that I know A, I can interpolate for all of these different properties. I can find U, I can find H, I can find S, and I can find specific volume. And the way that I do that is I take the lower value plus A times the higher value minus the lower value. And that's the equation that I have here. So I use that equation. I know everything now because I know A is 0.5. I put all this stuff into my calculator and I find a value for specific internal energy. I had a good question in office hours today that was like, how do I know how precise I need to make this measurement? Right? How many decimal places should I leave here? Right? And part of this is sort of just, this is why you pay engineers in real life, because you have to know how precise you need to be. But it's important to know what real precision is and what's kind of like faux or fake precision. right? It's kind of like cooking. You want to sound fancy, you say the word in French, right? Like nobody wants to eat snails, but escargot sounds, fancy, right? So here, or caviar too, right? Like fish eggs. I don't know. That's not. Although salmon roe, I like sushi. I miss having sushi. So eventually, I'm gonna have a lot of sushi, right? So a little salmon roe is okay, but I don't know about big fish eggs. Seems kind of gross to me, right? So here, now you know a little bit more about my taste in cuisine, right? So, right. So here, right, we're trying to interpolate between these two values, right? But we want to know how much precision we actually need, right? And the numbers that we start with only have one decimal point. So if we added any more than that, we'd kind of be lying about how precise we know that number, right? So here, what we do is we take at most one decimal point in this value. Now I rounded up a little bit higher than that, right? Which is probably going to be okay on a number that's 3,000. To be off by 1 over 3,000, right? That's going to be like 1/3 of a percent, right? So, it's probably going to be okay, but it's very application specific, right? I don't know if anybody watched over the weekend, right? But I watched some of the footage about, SpaceX sending astronauts up into space. So their margin of error is potentially less, especially when they take the booster rockets that they drop off and then they land over on that barge, right? Like that's probably a bit of a tough problem, right? So their precision on that application, might be a little bit higher than, in other particular applications where, accuracy is not as much, right? So that's part of justifying your first world salary as an engineer is trying to figure out how much precision you actually need, right? So here I have a value for U1. I can use this same formula because if I'm doing this linear interpolation, the beauty of doing it this way is that the equation always looks the same, right? So that's why I encourage you to set the problem up the same every time, because then you can just use the same equation for every single property, for every single problem, right? So we can do the same thing for specific volume and for specific enthalpy. So I can take those values now and I put them into my table, right? So here, it's a little weird because they ask me for the quality. And quality only makes sense if you're under the vapor dome. We're not under the vapor dome in this case, right? So here, instead of putting a value for quality, I put SHV to remind myself that this is a superheated vapor. And I also, in this case, I reminded myself that I found the answers on table A4. Next, I have to plot these things, right? So on my PV diagram, now I know my pressure and I know my specific volume. So the nice thing is here, I'm intersecting in the superheated vapor region, which is where I think I should be. So that's good, right? So that, increases my confidence, right? I also have a temperature and I have a specific volume. And those two things meet here as well. So it's nice that, through my analysis, I figured out what phase it is, and I get that same phase when I'm plotting it on the curve. So that's nice, right? That builds our confidence. So next, we want to do state 2, where we have a pressure and a quality, right? So this, we know for sure we can fix this state. So first, we know it's going to be two-phase because they told us the quality. Quality only makes sense if you're under the vapor dome. So when they tell you quality, it means that you're under the vapor dome, right? So quality is given. So I'm going to go to table, it says A3 here. I always confuse A2 and A3. One of them has pressure in the left-hand column. One of them has temperature in the left-hand column. So I may have got this wrong. But here, because I know the pressure, I'm looking for the table with the pressure in the leftmost column, right? So now here, I know that this is my pressure. And I know my quality is really close to 1, right? So we know we're under the vapor dome, but we should be pretty close to the saturated vapor values, which have subscript G. I also here automatically, right, because temperature and pressure are dependent under the vapor dome. So because I have a two-phase mixture and I know the pressure, that means I know the temperature already. I can just put the temperature in at 165. It doesn't matter what the quality is. That's what the temperature is if I'm under the vapor dome. So now, for all my different properties that aren't temperature, which I just know automatically, I can use this equation for quality, which is really the same equation that we use when we're doing linear interpolation generally, right? It's just that quality is like A. It's an interpolation factor that only goes from 0 to 1. So I use the letter Z here just to act as a placeholder for any property that you want to use, right? So here I can do this equation for a specific volume. But the thing that I always got to remember, like anytime you're reading specific volume off the tables, your spidey senses start tingling, right? The hairs on the back of your neck are standing up. And you remember that this number is not actually 1. It's been multiplied by 1,000 so that they could put it on the table without a whole bunch of decimal points. That means you have to divide it by 1,000 to get back to where the actual value is only for VF. Right? So there is no equation for there is no column for VFG. So we'll have to do that subtraction, VG minus VF, all by ourselves. In this case, right, if you were on a test and you wanted to go fast, right, VF is always very small compared to VG. So you can probably just use VG instead of VFG, but you're more accurate if you actually do the subtraction. Right? So here V2 is going to be VF plus X times VG minus VF. This should be a lowercase v over here. We read our numbers off the table. We put them into our calculator, and we find a value for the specific volume at state 2. And I got 0.2703. So I can look at that number, and I can say, wow, that makes sense, right? Because my quality is really, really high here, almost 1, and my value is very close, much closer to VG than it is to VF. VF is almost 0 here, right? So VG is just about equal to V2. So that's good. I have some confidence in this number. I can do the same process for all the other properties, right? So I write out the same equation for U2, specific internal energy. Again, they don't give me a UFG, so I got to work this out by myself. I get a value here, 2339.7. That's pretty close to UG. For H, it's a little easier because we can put HFG in here. So it's like one less thing I can mess up putting into my calculator. And again, I guess if I'm going to make a mistake here, it might be that I forget that this column is here, right? So maybe I would just write this down if I thought this was HF and I thought this was HG by mistake, right? So I could mess it up that way, but they're trying to help us here, right? And again, I got a value for H2 that's pretty close to HG. So I feel pretty good about these values. I put them into my table. Here there actually is a quality, and I used table A3, which was the one that had pressure in the left-hand column. I got to draw again, right? So here I know the pressure because it was given, and I know the quality is really high, right? So I draw my point here pretty close to the right-hand side of the vapor dome where quality would be equal to 1. And I put my point there. Because I'm under the vapor dome, I know the temperature was 160, right? That was the saturation temperature or something close to 160. So I can fix the temperature here. And then again, I know my quality is very high, so I can put my point on there. And both of these points fall under the vapor dome, so I feel pretty good about drawing them on the maps. Next, I move to state 3. State 3 looks like state 1 in that I have temperature and pressure. The temperature is pretty close, but the pressure is like more than 10 times less. So let's see if we can figure this out, right? So I'm going to guess that it's superheated vapor, but I could be wrong, right? So here I'm going to look in the superheated vapor table first, right? Normally I would look in the middle, in the two-phase region, but here, because I did one that was kind of similar, I'm going to guess that it's superheated vapor. Now here, for a pressure of 7 bar, on this superheated vapor table, it tells me what the saturation temperature is for 7 bar, right around 165 degrees. And in this case, my temperature is 440 degrees, which is a lot bigger than 165 degrees. So that means at this pressure, I'm past the boiling point, so I would expect to have superheated vapor again, or steam. Right? So here my temperature is 440 degrees, and I'm lucky, or I'm thankful here, that I have a row that's 440 degrees. So I don't have to do any interpolation here. I just read the values off this line, and I get specific volume for 3, specific internal energy for 3, and specific enthalpy for state 3 as well. I track my units in all of these cases. And, so here on table A4, they always tell us the units right up at the top here. So I put all that information here. Again, it doesn't make sense to talk about equality here, so I write SHV for superheated vapor. You could also just put a line here, or NA or something like that, right, for not applicable. State 4 looks a lot like state 2 because it tells me quality, but in this case, I'm told the temperature and not the pressure. So it's a two-phase mixture. I know that already because they told me the quality, but I'm not going to use the same table I used last time because this time I know the temperature and not the pressure. Oh, sorry, I forgot. We got to draw these things for the last one, right? So we knew that the pressure was much lower than before, but it's still got some high temperature, right? So the temperature line is going to come down like this, right? And it's going to cross this line somewhere over here, right? So here we have, again, we're off into the superheated vapor region above the vapor dome, above the red line. We have a high temperature here, 460, and we know the specific volume, so we can draw that up. And here again, we're in the superheated vapor region. Notice that these points, they don't land in the same spot on the two different graphs, right? Because they're different graphs. But they should always be in the same region. Like we see here, we have both of our points are in the superheated vapor region. Now, it can happen that when you're drawing these yourself, you get to a point where they're not in the same region. And that could be just because, this one is nice because it's drawn to scale. Maybe yours is not drawn to scale, so your vapor dome's not in the right place or something, right? Or it could be that you made a mistake somewhere, right? So you do have to think about it a little bit and try to reflect. So now we can go to state 4, which we know is two-phase, right? So we know it's two-phase because we're given the quality, and we're also given the temperature. So we need to look on the table here that has temperature as the leftmost column. And in this case, our temperature is 40 degrees. So I already know the pressure because it's two-phase and it's 40 degrees. But for all the other properties, we're going to use an equation like this, that the property we're looking for at the given quality is VF plus X times VG minus VF. Again, that should be a lowercase v. Right? So I can do this for specific volume. I can do this for all of the different properties. Right? And again, I'm expecting a value between, remember this is 1 over 1,000 and 19.5. And because the quality was still pretty high, I think it was, here it says 0.93, right? Almost 0.94. Then, we should be much closer to 19 than we are to 1 over 1,000. And we see that in our final answer of 18. And I should have my units here. This is meters cubed per kilogram because I'm reading it from over here. I can do the same thing for specific internal energy and for specific enthalpy. So the process here is the same as it was for, I think, state 2, where we had a two-phase mixture, right? And again, even our quality is still pretty high. So here we got to draw this out. So we know that our pressure is still pretty low. We know that our quality is relatively high, so we're closer to the red line than the blue line, right? Or in this case, because it's the scale, I can just draw my specific volume on this graph, and I find my point. It's under the vapor dome, which I like, right? That's what I expect, and it's closer to the red line. I do the same thing for temperature. We have a lower temperature here, but we still have our specific volume, and it was just under 19, and we know that the point should fall under the vapor dome, and it does. Next, we come to state 5. The tricky thing about state 5 was that it didn't outright tell us what the quality was. Instead, it told us it was a saturated liquid. And because it's a saturated liquid, again, that spidey sense should start tingling, and we know that's code, right? That's secret engineering code for x is equal to 0. So here our temperature is still at 40, but we're liquid, right? So if this was a process, this is some kind of cooling process going from temperature of 40 and mostly vapor, cooled down to the same temperature, but all liquid. So my quality is equal to 0, which means anytime your quality is between 0 and 1, including 0 and 1, I would use those tables A2 or A3, depending on if you knew the temperature or the pressure. Right? So X is given, but in words, right? Not in a numerical value. And X is equal to 0. Right? So that means that it's a saturated liquid. Right? And saturated liquids are great because now we don't have to do any kind of interpolation. So we know we're saturated, right? So temperature of 40 degrees, we're saturated, so this is the pressure, right? And now I just pick off the values that have a subscript of F. So if I want the specific volume, it's VF. Remember, we got to divide this by 1,000. If I want the specific internal energy, it's UF. If I want the specific enthalpy, it's HF. And if I want the specific entropy, which we're not looking up in this problem, but if I did, it would be SF. So in this case, right, because in my equation, it's always, for example, VF plus X times VG minus VF. But if X is equal to 0, it's just VF, right? So I'm basically just reading these numbers off the table where I say, oh, V5 is VF, U5 is UF, and H5 is UF. So that's good. I have all these values, and I can just put them in. I got to draw this again. So here I know my pressure is really, really low, right? Because over here, I looked at my temperature was known, and I was under the vapor dome, which means that I know this pressure. It's pretty low, right? So here I can look on this table, and I draw a very low pressure line, and I know quality is 0. So it's where this orange line intersects with my blue line for saturated liquid, right? So it's right there on the blue line. Similarly, I knew that the temperature was 40 degrees, and this orange line intersects with the saturated liquid line here. So this is good. I'm almost done. I just have one state left, and this is the state that's the most different, right? So here, we need to know the pressure, or we're given the pressure, 80 bar, so we're back up to a high pressure. And I know the specific enthalpy, H. So now we have a pressure and an enthalpy. How do we fix the state? This is different than all the other properties. So the first thing that I want to ask myself is this a two-phase mixture? Right? So how do we fix the state? Is it a two-phase mixture? So what I'm going to do is I'm going to go to the two-phase table where pressure is on the left. My pressure is 80 bar, right? And if my pressure is 80 bar, if I'm a two-phase mixture, I have to be between HF, which is like 1316.6 kilojoules per kilogram, and HG, 2758 kilojoules per kilogram. So I look on this table, 80 bar is there. So I'm not above the critical point. So it is possible that we're under the vapor dome. Right? So now I want to see, is H6 between HF and HG? Right? So now I know HF, right, is 1316.6 kilojoules per kilogram. HG is 2758 kilojoules per kilogram. The problem told me H6 is 181.94 kilojoules per kilogram. So it's important here because we're off by more than a factor of 10. My first thing to do would be to check the units, right? So that it's not in megajoules per kilogram or something funny. But the units are the same. And here I see that H6 is much less than HF, right? So as X increased, right, as I transition from saturated liquid up to saturated vapor, enthalpy increased, or specific enthalpy increased, right? And if we kept going as a superheated vapor, enthalpy would continue to increase. And if we moved, the other way from saturated vapor down to saturated liquid, the specific enthalpy is decreasing. And if we cooled further to a subcooled liquid, H would continue to decrease. So because H6 is less than HF, that means we're a subcooled liquid, right? So if on this diagram, if H6 is less than HF, then that means you're subcooled liquid. If H6 was greater than Hg, then you would be a superheated vapor. And if HF was in between, or in H6 was in between HF and Hg, then you would have a two-phase mixture. But in this case, H6 is below HF, so we have a subcooled liquid. So we're in this subcooled liquid region. And that means we have to use table A5. So here we have 80 bar. And the problem with subcooled liquids, one of the things that's unfortunate is that the data is pretty sparse. There's not a lot of tables in here, so it's a little bit unlikely that you're going to find a subtable with the right pressure. So when you have a subcooled liquid, you're almost always going to have to do a double interpolation, right? So in this case, we need to make our own table, right? So we can see that the temperature will be between, here you can see the temperature will be between 40 and 80 because our value of H is in between these two numbers and in between these two numbers. So I don't have to recreate these whole tables, but I do have to make myself my own table for 80 bar with these two rows. Right? Now, you can tell that I don't like doing this because there's a lot of arithmetic involved here. And because I drew a little sad face over here. So, hopefully it's obvious I don't like doing this. We're going to learn some tricks about what to do with subcooled liquids. But until then, we're kind of stuck with double interpolation. So we're going to make our own table here, right? So first, we're going to interpolate with pressure, right? So we know we have to go between 75 bar and 100 bar, and we're at 80 bar, right? So I can find my interpolation factor here, and it turns out that it's 0.2. I'm 20% of the way between 75 bar and 100 bar. So that means for any property that's on this table, if I want to interpolate between these two tables with pressure, I use this equation, right? Z at 75 bar is equal to A plus Z at 100 bar minus Z at 75 bar. So what I want to do is I want to make my own table, right? So I do this here for a specific volume, right? So this is this table here, this is at 80 bar for 40 degrees and 80 degrees. I'm eventually going to have to interpolate between these two rows as well. But for now, I'm just trying to take this data and this data and make my own 80 bar table, right? So here I can find these two values for 80 bar at 40 and 80 degrees Celsius. I can do the same interpolation for specific internal energy. And I see that it's going to run from 166.6 at 40 degrees to 444 at 80 degrees. And then for a specific enthalpy, where it runs between about 175 and about 341. So now I have my table, but I want to be in between these two numbers, right? So it's good. My value of H is in between 174.6 and 341.2. Right, so now I'm kind of at the point I would have been if they would have put the right table that I needed in the appendix, right? So now I got to make my own row on this table that fits somewhere in between 40 degrees and 80 degrees. Or maybe more specifically, in between 174.6 kilojoules per kilogram and 341.2 kilojoules per kilogram, right? So I'm at 181.95. So now I got to find my interpolation factor B. So my interpolation factor B is going to be H6 minus H at 40 degrees divided by H at 80 degrees minus H at 40 degrees. So I can put these numbers in, 182-ish minus 174.6 divided by 341.2 minus 174.6. And when I do this, I get that I've traveled just under 5% of the range. if this was a test, I would probably have done this calculation and said, look, Professor Schertzer, it's 4% of the range. I'm just going to take the values over here at 40 because interpolation takes a long time and these numbers are going to be pretty close. And if you did that after writing that sentence, then to me you would have displayed your understanding of how to do this, right? But if you would have, even if you thought this and just wrote down the values here at 40 degrees, but you didn't write down that sentence, then I have no idea if you know what you're doing or you just got lucky, right? So, help me out, right? This is one of these kind of help me help you kind of things, right? So if you write down what you're doing and why you're doing it, then I'll see that you understand the question, right? And that's what I have to grade on a test or on homework is I'm grading, did you demonstrate your understanding, right? Because there's no way for me to actually know if you understand it or not, right? So you have to sort of tell me why you're doing what you're doing. So we can use this interpolation factor, which is just under 5%, right? And we can find the temperature, right? So this is going to be, 4.5% of the range. So I'm at 41.76 degrees. So I can put that on my table. I can do the same thing with specific volume, right? Remembering again that these numbers have been multiplied by 1,000. I even wrote that on my table here. So this is still, again, 1 divided by 1,000. And I can do it also for specific internal energy, and I get just under 175 kilojoules per kilogram. So now I filled out my whole state table, right? This last one was a little bit rough, right? A little bit longer to do, right? Because it's this double interpolation. Like I said, we're going to use some tips and tricks to kind of short circuit that process to make life a little bit easier. But for now, we know that this double interpolation is potentially something that we need to be able to do. We fixed all the states. We haven't plotted them all yet, right? So we do have to plot this other state. So we know it's going to be subcooled liquid. Let's see if that's what our data tells us. We know the pressure. We know the specific volume. So in this case, we did get our 0.6 in subcooled liquid on our PV diagram. We know the temperature. And we also know the specific volume. And again, we're over here to the left of the vapor dome. And that's what we want to be when we're subcooled liquid. So this kind of makes sense. Right? So at the end of the problem, we say, does this problem make sense? Do our answers make sense? Right? We can't prove they're right, but hopefully we can't prove they're wrong either. So we check our units all the way throughout the whole problem. We checked our units. When we were trying to find specific volume, we got meters cubed per kilogram. When we were trying to find specific internal energy or specific enthalpy, we got kilojoules per kilogram. So that's good, right? And the other thing that we did is, even though I really have no conception of whether any of these numbers are correct, I don't have a feel. Maybe some people do, but I don't have a feel like, oh, that's the temperature and pressure of my liquid. I bet that the specific internal energy is, 1,042. I don't know. But I do know that when I plotted them all on the PV and TV diagrams, I got that all my points were in the right part of the table that I thought they were going to be based on the phase that I thought the material was at. So again, I can't prove that my answer's right, but I also can't prove that it's wrong. And that gives me some confidence that I'm at least moving in the right direction, right? So, sometimes that's the best that we can do before we sort of test something out, either numerically or in sort of a scale model or something. So again, applying intuition, I'm not sure how much intuition I have about whether or not the numbers are right, except for the units were correct and I got everything in the right phase, or the phase that I thought we would be in. So that's all that I had for today, but I'm happy to entertain questions if people have questions either about sort of the examples that we did today, or maybe even about the homework or something as well. All right. Well, thank you very much. I hope that the audio quality was better this time. And if we continue to have issues, please let me know, and we'll see if we can get solutions to those problems. Thanks very much. Remember that your homework will be due by tomorrow at midnight in whatever time zone you're in. Thanks very much and stay safe.